So in this third chapter, we're going to get into a couple of numerical things of matrices, transposes, and determinants. The first part is the transpose of a matrix. Let me just tell you what it is first, and then we will define it. Basically, it just means you swap the rows and columns of a matrix. Fairly simple. So if you have an m by n matrix, m columns and n rows, when you transpose it, it becomes another matrix of n rows and m columns. Columns become rows and rows become columns. So every element in the ith row and jth column will become an element in the transpose in the jth row and ith column. So if A is a 3 by 4 matrix, 3 rows and 4 columns, then A transpose will have 4 rows and 3 columns. So there you go. There's an example. Each column in the first matrix has a color associated with it, so that you can see that when you transpose it, those columns just become rows. Now, as you know, a vector is merely a small matrix. It's a matrix of one column. So when you take a transpose, it becomes a one row, a single row matrix. So if X is in Rn, you don't write Rn by 1, you just write Rn. Then X transpose is going to be in R1 by n. There you do write 1 by n, you cannot just write Rn. So here's an example. 7, 5, 6 in a column is a column vector. When you transpose it, you get 7, 5, 6 in a row, is a row matrix. Some people do call it a row vector and develop linear algebra machinery based on it. We won't do that in this course. Actually, this definition of a transpose of a vector, we did use it earlier while talking about a dot product. So x dot y is x transpose times y, which is conformant for multiplication because x transpose has got one row and n columns, and y will have one column and n rows. So the number of columns of the first matrix x transpose is the same as the number of rows of the second matrix y. In this special case, x dot y is the same as y dot x. So x transpose y is the same as y transpose x. This you can convince yourself by taking an example or just by looking at the formula whereby you have the row column multiplication of the matrix. You will see that it's just some product that is accumulated product, and that's going to be the same whether you multiply the first one or the second one first. So let's actually try to define it. In order to define a matrix transpose, you have to define something called the main diagonal, also called the leading diagonal. So those would be the collection of elements with the same row number and the column number. In this matrix, which is a white matrix, you have 7, 8, and 2 along the main diagonal highlighted there. And when you transpose it, 7, 8, and 2 remain on the main diagonal. Everything else gets flipped around, gets reflected about the main diagonal. And that is the definition of a transpose. Now, when you think of a diagonal, ideally you might want to think of a square matrix, but then the concept of a main diagonal is defined not merely for square matrices, also for all kinds of matrices. It's just that you go to the right and to the bottom to the extent possible. In the case of a wide matrix, as you see in this matrix, you keep going right and down and right and down and right and down until you hit the floor. You cannot go any further. At that point, you say that that collection is the main diagonal. Similarly, if the matrix is tall, again you go to the left and then down to the left and down to the extent possible until you hit the right wall. A fairly simple concept. So like I said earlier, if A has m rows, then A transpose will have m columns. M and n, m rows and n columns will become n rows and m columns. So the definition of the main diagonal, also known as the leading diagonal, is a collection of elements with the same row index and the column index. So start from the first row, first column, go to the second row, second column, and so on. Go diagonally down and to the right as far as possible. Now, we're kind of introducing a new notation for a matrix. As you know, Aij is a typical representative element of the matrix A in the ith row and the jth column. Now, if you were to write it, expand it as a matrix, then I'll have to write A11, then dot, 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 dot this way, and the ith row Aij, that will be a huge equation. So I'm going to kind of simplify it and then write it with square brackets around Aij, and that will stand for a matrix in our book. So this may not be a standard notation, but this is something that I use now and again if I want to write a representative matrix to say that its typical element is Aij. I want to use it and I want to write that in one line rather than in a display equation, and this is what I will do. Not a biggie, but keep that in mind. Now the formal definition, as formal as it can get, is that the transpose of a matrix has its elements flipped, or reflected I should say, about the main diagonal. Now we have a bunch of properties that we need to learn about the transposes. The transpose of a transpose is the original matrix, and that is kind of obvious. You're flipping it, rows and columns, then swapping them again, rows and columns, then you get the original one. Then the next one that is a bit less obvious is that the transpose of the sum of two matrices is the sum of the corresponding transposes. A plus B, the whole thing transposed, is the same as A transpose plus B transpose. This you can see just by thinking about the matrices as table of numbers, and then you can see that when you transpose it, you transpose both, and they're the same as transposing first and adding it. Not that complicated. And the fact that scalar multiplication commutes with transposition also is something to keep in mind. What that means is that if I take a matrix and I want to scale it by, let's say, number 2, double every element, then take the transpose. It's the same as transposing the matrix first and then doubling every element, obviously, because scalar multiplication of a matrix goes and multiplies every single element. So it doesn't matter whether you do it before or after doing the row column swap. Then another one that we have to keep in mind is that a scalar is its own transpose. A scalar can be thought of as a one-by-one matrix or a single element vector and so on. So the transpose of the scalar is a transpose of a one-by-one matrix. One-by-one matrix has got only one element, that is the main diagonal. There's nothing to flip, so you get the same thing. So S transpose is S. Now the most important thing that you will learn here is that the transpose of a product is a product of the transposes, but in the reverse order. That is called the product rule of transposes, and that is very important. So A, B transpose is B transpose, A transpose. So we will go through that. We'll spend a couple of minutes on this one because this is important. So let's take an example first. So A is a 2 by 3 matrix, 2 rows, 3 columns, and B is a 3 by 2 matrix. So what's the size of AB? It's going to be 2 by 2. So you can actually do the multiplication. So the first element in the product in this location is 1 times 3, that is 3, plus 2 times 10, so 13, plus 3 times 7, 21, so 13 plus 21, 34. And like that you can find each one of them. Now transposing is just swapping these two guys, so you get 40 there and 79 there. The main diagonal doesn't move, being the mirror. Now if you compute B transpose A transpose, you will get the same thing. So this is just an illustration, an example of the product rule. So you can see that those two guys are the same, the highlighted ones. Now before actually looking at the proof of the product rule, let's think about the conformance requirement. So in order to be able to write A times B, you have to have the number of columns of the first matrix being the same as the number of rows of the second matrix. So AB will be in M by N because the inner indices will kind of get summed over. Then if you look at AB transpose, that is going to be in N by M, N rows and M columns. Now if you take B transpose, that is in N by K, A transpose is in K by M. So B transpose A transpose will again get the inner index getting swallowed by the multiplication, and then B transpose A transpose will have N rows and M columns just like here. So these two guys are the same. So this is not a proof, this is just saying that product rule has at least a chance of being right because it doesn't violate the conformance requirement. That's not, of course, enough. Let's look at a proof. The first proof, first of all, let's say that C is a product of the two matrices AB, so C equal to AB. Now let's use a notation A prime for A transpose and B prime for B transpose and C prime for C transpose, just to make the display a bit easier. So by the definition of the matrix multiplication using dot products, you know that the ith row of A and jth row of B, the dot product of those two things, will be the ith row, jth column of the product C, Cij. Cij is going to be Ai dot Bj, ith row of the first matrix, jth column of the second matrix. And by the definition of the transpose, Cij prime, which is the ith row, jth column of the transpose, is going to be the jth row of A and the ith column of B, because C prime ij is the same as Cji, so jth row, ith column, jth row of the first matrix, ith column of the second matrix, and that turns out to be Bi prime dot Aj prime. Why? Because the ith column of B is the same as the ith row of B prime, because B prime is B transpose, so the rows there are the same as the columns of the original matrix. Similarly, the jth row of A is the same as the jth column of A prime, because A and A prime are transposes. So now you can look at this and you can rewrite it. So I'm taking the ith row of B prime and the jth column of A prime, so it's B prime times A prime in the matrix form. Recognizing the right hand side in step number 4, B prime is just B transpose, A prime is just A transpose, so you can just write that. That is what the right hand side says. And C prime is just C transpose. That's what the left hand side of step number 4 says. And what is a C? C is just AB, so C transpose is AB transpose. So that's the proof. It's a bit tedious, and if that was tedious, the next one is even more tedious. That's by looking at matrix multiplication using the row column picture, meaning the row of the first matrix and the column of the second matrix getting multiplied in the sum product fashion. So it's a cumulative sum. P is a running index, so ith row and jth column, P will get summed over, and then you get Cij. This is actually the same as writing the dot product, just that dot product is a little bit easier to write, but the arguments are absolutely the same. So I will not go through this. I'll leave it to you as an exercise to understand this using the previous proof and the equivalence of this summation being the dot product. The next one to do is to actually use transposes and look at matrices with special shapes or special properties, and that will be the next video.